So we stopped here. We didn't get started. We just kind of looked at what was going on and kind of formulated a plan, and then we stopped. Okay. So real quick again, students wondered whose Instagram account gets more likes on average, Katy Perry's or Justin Timberlake's. Okay. The students selected a random sample of 15 Instagram posts from Katy Perry and a separate random 15 Instagram posts from Justin Timberlake, and recorded the number of likes from each post. Here are the dot plots of the data and summary statistics. Okay, so we said X bar for Katy Perry is 7,193. X bar for Justin Timberlake is 6,393. Standard deviation for the sample standard deviation for Katy Perry is 1,749. Sample standard deviation for Justin Timberlake is 3,170. Okay, says exactly what the table says, but it's just we use symbols instead of words. Okay, does it make sense that Justin Timberlake's standard deviation is almost double what Katy Perry's is?
Yeah.
Why?
Because the data is way. Yeah, look at the graph, man.
What about the graph?
The data points are way farther or way scattered around.
It's more scattered, right? The data points for Justin Timberlake, the range is wider. Range measures biggest minus smallest. That's bigger. And then within the range, there's a lot more spread, right? Okay, so question says, construct and interpret a 95% confidence interval for the difference in the mean number of likes for Instagram posts from Katy Perry and Justin Timberlake. Okay, so we have two sample. We have one for Katy Perry, one for Justin Timberlake. So what we're going to do is we're going to have two population parameters. Okay, so we start the true mean. For both, we're going to start the true mean. And then how would we go for Katy Perry? Or what would we go? True mean.
True mean likes Katy Perry gets on her Instagram post.
True mean number of likes, yes. That Katy Perry gets on her Instagram post. Okay. So it'd be the same thing for JT, except it's just instead of Katy Perry, you write Justin Timberlake. So it'd be true mean number likes that Justin Timberlake gets on her, on his, I gotta change that word too, his Instagram posts. Done. Okay. Population parameter, that's done there. Let's see, so now we have test statistic. We don't have to do an hypotheses, any kind of hypotheses, because this is an interval. Okay, so earlier we talked about the formulas. So here's the formula here. That guy right there. All right. We said that this part right here is on our sheets, is on our the back side of our formula sheets. That's on there, so we don't have to memorize that. We just have to figure out T critical. We have to figure out X bar 1 minus X bar 2, or JT and KP. Doesn't matter who you put first, who you put second. It does not matter. Just stay consistent. Okay. So if I put X bar Katy Perry minus X bar Justin Timberlake, I just have to stay consistent the whole way through. If you switch them, that's fine too. You just stay consistent. Plus or minus T critical. And then I have standard deviation. So it's S1. So that's going to be for Katy Perry squared. I have to square that. and then it's N for Katy Perry. Plus, let me verify that real quick. Let's see.
Is that a square root?
Yeah, square root, yeah. So it's S1 squared over N1 plus S2 squared over N2. Okay. So it's going to be S squared for Justin Timberlake over N of Justin Timberlake. And then, yep, square root, all under the square root. And then we also use degrees of freedom. We're going to have degrees of freedom on this one. How many, what was the formula that we used that I told you guys to use to approximate degrees of freedom?
Oh, that's good one. Oh, wait, you mean the
Not that one. The calculator will do that one for us. Minus close, not
the smaller.
smaller n minus 1. Smaller.
Okay, 15, so it doesn't matter.
If they're both the same size, then it doesn't matter. But if the one's minus one's bigger than the other, use the smaller n minus 1. Okay? That'll help us with getting that number. T crit. Okay. Next thing is conditions. Oops. Yes.
Would you need to include that DF thing with your test statistic, like on the test?
I can't remember if they require it. I do it just to be sure, but I can't remember if it's required. I gotta double check. I gotta double check if DF is required. Okay, so here we go. Condition. Okay. So I'm going to check for KP, and I'm going to check for JT. So number 1, SRS. So how were those 15 posts selected? How were those 15 posts?
Randomly.
They were randomly selected. Okay, so we can put stated. Okay. Number 2, 10% condition. Oops, that's number 2. This is number 1 still. Okay, so little n is less than 10% of big N. It's going to be the same for both. Or no, it won't. Sorry, no, it won't. Similar, but it won't be the same. So little n is 15. So 15 is going to be true for each of those. Okay, so we don't have a number for big N. So what do we write in there instead? Yep. All KP IG posts. All JT IG posts. Okay. It's a number you can calculate, but since they don't give it to us, we won't calculate. Okay, last one is normality. Okay, so how do we figure out what are the options for this specific condition number 3?
It tells you over 30 or you make a graph.
Population is normally distributed. They tell us in the prompt. They don't tell us in the prompt, but the number is big enough. It's over 30 for each group. Each group has to be over 30. Combined, it's 30, but it has to be for each group. Okay, not combined. B, our last one, graph both sets of data. Are there any outliers? Okay, so it looks like we're gonna have to go with number 3. And luckily they've given us a graph. So let's go look at the graph to see what we see. Okay. So we already have a graph, so we don't have to graph this. You guys don't have to graph this, it's already graphed. The dot plot is one of the options. Dot plot or box plot. I always do box plots because that'll also tell you about outliers. But just looking at the graph, do any of those blue dots look like they could possibly be outliers? No.
The farther right Justin Timberlake?
This guy right here?
Yeah.
It's far,
But is it that
but
far?
but is it that far away from everyone else? No. I don't consider it that far away from everyone else. You're talking about, this is 5,000 posts, right? The difference here between 10 and 15 is 5,000. So you're talking this one's probably 11, between 11 and 12, and this one's about 13. So that's not that far away. To be an outlier, it would have to be, remember the formula, it would be, to be an outlier on the big side, you would have to go, it would have to be 1.5 IQRs above that. IQRs are the middle 50%. So wherever the middle 50% of the data is. So if there's 15, the middle 50% would be around 7. So we're the middle 7. 1, 2, 3, 4, 5, 6, 7. So probably in the middle 50% would probably be somewhere. Nope, probably shifted this way a little bit. Probably be around here somewhere. Middle 50%. Let's see. 1, 2, 3. 1, 2, 3. 1, 1. Yeah, so probably somewhere around here, the middle 50% would be. From 3,000 to 7,000, that's 4,000, right? So in order for something to be considered an outlier, it would have to be 1.5 IQRs. So that's 7,000 times 1.5. You're talking 10,000, 11,000. So this dot over here would have to be 11,000 away from that. And that's not enough. That's not enough. Okay. It is definitely, there is some room there, right? But it's not a big enough to be considered an outlier. Okay. So we would say dot plots show no outliers. Or no outliers appear present. That's probably a better way because we're not actually calculating it. So probably be better to say dot plots show, or dot plots appear to have no outliers. That would probably be a better way to put it.
And my phone's dead.
Okay.
I sent it to phone dead. I couldn't even finish my room. I'll bring a charger tomorrow.
Okay. All right. Let's see. Let me add another page. Okay. After that, we have calculations. Okay. So we're going to use X bar Katy Perry minus X bar Justin Timberlake. Or if you did whatever you did here, that's what you have to keep it consistent with. Whatever you did here. So if you did the opposite, that's fine. Do the opposite. But just keep it consistent. Okay. So KP minus JT. So we have 7,193 minus 6,393. Yep. Okay. That's the difference, plus or minus T critical. What is T critical going to be for this one?
2.145.
How'd you get that? How did you get 2.145?
95% confidence interval of a DF of 14.
So we want to put DF of 14. Okay. Make sure you note degrees of freedom. So degrees of freedom 14 for 95% confidence interval, 2.145. 2.145.
Who comes up with these formulas?
All right, so here we go. S1 squared, S1 squared, or Katy Perry squared, Justin Timberlake squared. They're both over 15 because they're both sample sizes are 15. So here we go. Gonna have some big numbers. 1749 and 3470. And then the big square root. Now from here, you can crunch those numbers. There's nothing wrong with that. You can crunch them. It's just a lot of adding, dividing, multiplying, square root. Any regular calculator, any scientific calculator can do it. Or in the slide here, it shows you, I show you the steps. It's the same steps we've been doing. The hard part is just which formula, not which formula, but which test do I choose from the list on my calculator. So the list on my calculator, let's see. So stat, test, through all the intervals and tests are. For calculus. Okay. Which tests are we going to choose? The one after 9? Saying the one after 9? Yep. 2 sample T interval. It's not a proportion, so it's not 2 proportion. It's 2 sample T interval. Data is if I have the actual data in L1 and L2. I don't. So I'm going to go stats. I don't have the data, but I do know enough about it. X bar 1. X bar 1 was 7193. Standard deviation 1 was 1749. That's for Katy Perry. And her sample size was 15. Justin Timberlake, 6393 and 3470 for standard deviation, and his was the same size. 0.95. Here is where I was looking for pooling. We never, ever, ever pool with means. We only pool with two proportion tests and intervals. Okay. So, nope. Calculate. So we get negative 1,288. No decimal. And the second one is 2,888.5. There's the degrees of freedom. See the degrees of freedom right underneath the interval here? That's them utilizing the calculator, utilizing that one that we talked about. This guy here, the ugly, where is it? This guy right here. Okay. Even that, though, is still an approximation. It's a closer approximation than ours, but it's not that bad. Okay. So we estimated degrees of freedom at 14. They estimated a little bit higher, about 20, 21. Okay. But if you look at your degrees of freedom, if you look at your tables, look at your tables real quick. Look at your tables real quick. Let's look at the difference. Let's see where my table's at. Where are my tables at? Those are Z tables. I want T tables. So if you look at T tables, for 95, right? So 95 is right here. That's a 95% confidence interval. Look at the degree for degrees of freedom of 20 versus degrees of freedom of 14. Degrees of freedom of 14 is the one we used. Degrees of freedom of 20 is right there. You're talking about change. They're not off much. They're off not even a tenth, half a tenth. What's half a tenth? 100th. They're 100th difference. So, you know, and then the calculator, on top of that, the calculator used the more accurate one. So, in other words, we're okay. Because some people freak out. I've had students say, well, the calculator used 20.6 something as a degree of freedom, and we said 14. That's way off. And I'm like, yeah, it is off, but I mean, their t-scores aren't that far off. And on top of that, to come up with this number, we use the calculator's degrees of freedom, right? So that's why we're okay. All right, last step is we have to conclude. Okay. Conclusion, we are 95% confident that right here, that the true difference in mean blank is between blank and blank. We are 95% confident that the true mean, sorry, true difference there we go. The true difference in mean blank. Oops. The true difference in mean blank is between blank and blank. Okay, so true mean what? What's the difference? What did this number represent here? What did this number represent? Because that's the difference. What did that number represent? Because that'll tell you how to write the rest. Whatever, this is the sample. If you can tell me what the sample represented, then you can tell me what the rest represented. So confident that the true difference in mean blank is between blank and blank.
And like each person gets on that.
Okay, so mean in mean likes Katy Perry. Katy Perry and Justin Timberlake. Get on their Instagram posts is between -1288 to +2888.5. What does that mean? Because often what they'll have you do is answer a question based off of that. So what does that mean? What does the whole thing mean? Like, why is there a negative number? Why is there a positive number? Why is there one negative and one positive?
Because sometimes Justin will get more likes on average, and sometimes Katy Perry gets more likes on average.
Kinda. You're close.
Oh yeah, I'm close. The first guess. Doesn't it mean that there's no true difference? Oh yeah, there's no likes.
Yeah, exactly. So the question that might come later is there evidence to show that Katy Perry gets significantly more likes on her Instagram posts? And just like Josh said, no. Because zeros in the interval. Good. That's one way. That's definitely an interpretation, right? That's why one number is negative and one number is positive, right? So if zero's in there, we fail to reject. We fail to reject that Katy Perry gets more Instagram posts or likes on her Instagram post than Justin Timberlake does, significantly more, right? She does get more. In this sample of 15, she got more. She got 800 more. But bigger picture, that's just on these 15 that I looked at. I'm looking at bigger picture. Bigger picture, all of her Instagram posts, all of his Instagram posts. Why is this important? If I own a business, I own a company, Coca-Cola, whatever company, I want to know who's going to get more Instagram posts. So when they post stuff on Instagram, I want to know who gets more between the two, right? This was written 5-10 years ago when these two were like very big stars. They're still well known, but they're not as well known as they were 5-10 years ago. So how does Coca-Cola know who to work with? How does what is the other company? Target, whatever, all these clothing companies, how do they know who to work with? They look at their stats. They look at their stats. And social media is one of them, right? Social media is one of them. Kim Kardashian, she is one of the most popular social media people in the world. But I guarantee you, if you go talk to 10 people, 7 of them would be like, I can't stand her. How do they know how to work with her? Because she has the most Instagram followers out of anyone in the world, right? That's it. There's no one else who gets more Instagram followers than her. So more people, more eyes are going to see that. More eyes are going to see posts. So if she posts something for Coca-Cola, if she posts something for whatever clothing store, a lot of people are going to see it, right? A lot of people are going to see it. So if I'm working with them, I'm like, hey, Katy Perry and Justin Timberlake, Katy Perry cost me $100,000 for one post to promote my company. Justin Timberlake only costs half that. Now, if Katy Perry is going to get significantly more, I'll invest that. No, not significantly more, right? Not significantly more. So I'll save my money, $50,000. I'll keep it, and I'll just go with Justin Timberlake. Okay, that's what that says. Okay, all right, all right. Okay, so let's look at. Let's skip. All right, we'll leave the last question for tomorrow. Let's go back. Let's go back to. There's one question at the end. We're not going to hit that yet. We'll get to it, but not right now. Sampling distribution. We have sampling distribution. So if they ask you about the sampling distribution, that means the distribution of all samples. So in the last question, if we were to take samples of 15 of her Instagram post and his Instagram post, what would those look like? Where would those dots be? Where, if I was to graph them, what would that graph look like? That's what they're talking about here. Okay. Actually, no, it's talking about the difference. So if I were to take samples from Justin Timberlake's post and Katy Perry's post and subtract them just like I did before, what would be true about their mean differences? Well, three things. Their mean difference, their sample mean difference is normal, the sampling distribution. When you see distribution, that's not just one sample, right? Down here, they took one sample of 15 and one sample of 15. I'm talking about infinite number of samples. If we were to keep doing that forever and ever and ever and ever and ever, taking samples of 15, what would the difference be in these two numbers for all of them? Okay, that's what I'm talking about when I say sampling distribution, not just one sample, many samples. Okay, if both is normal, if both population distributions are normal, it is approximately normal if both sample distributions are larger than 30, or if one population is normally distributed and the other sample size is large. Okay, so that's how you can tell. Normal if it's stated as normal, approximately normal if they're big enough, or if one is normally distributed and the other one is large. Okay, the mean and the standard deviation. So these are all. This is our number 3, our condition number 3. This is condition number 2 right here. Okay, and then an independent SRS, it's kind of a condition that has to happen for any of these to work. Okay, so I want you to use this to answer A, B, and C. A, B, and C on the next one. Okay, I'll give you 5-10 minutes. All right. A fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large drink cups. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid L dispensed by the machine follows a normal distribution with a mean of 27 ounces and a standard deviation of 0.8 ounces. When the medium setting is chosen, the amount of liquid M dispensed following a normal distribution with mean 17 ounces and standard deviation 0.5 ounces. To test the manufacturer's claim, the restaurant manager measures the amount of liquid in each of 20 cups filled using the large setting and 25 cups filled using the medium setting. So let x bar L minus x bar M be the difference in the sample mean amount of liquid under the two settings. What is the shape of the sampling distribution for x bar L minus x bar M? And why is it so? So which one would it be? Or what would it be, I should say, not which one. What would it be? What is the shape?
Normal.
Okay, because let's see. Okay, so it says, I see follows. When the large chose, the amount of liquid dispensed follows the normal distribution. Yep, that is true. So we would say normal.
It doesn't say that for the medium account, though.
It does. Yep.
Oh, this is
The second one I highlighted. Normal shape for each. Normal shape, not for each. I say normal shape because we're talking about just about the difference, but each one does, yeah. Because let's see, because let's see, how can I say this? There you go. Both settings are normally distributed, or yep, perfect. Normally distributed. Okay, find the mean. Okay, so if it's normal, they're both, or it's a normal shape, we would go x, oops. We would say we would say, let's see. So for this guy here, the sample, we would say right here, mu x bar 1 minus x bar 2 equals mu 1 minus mu 2. So we would say, since we're doing L minus X, or L minus M, what is L? 27 minus 17 equals 10. Okay, 10 ounces. Calculate standard deviation. Standard deviation. So standard deviation is right there. So standard deviation of the first one is 0.08 squared over,
0.08. It's not 0.8.
sorry, 0.8. I wrote down the wrong, 0.8, 0.8. N1, how many is our first sample? 20. Okay. Plus over 25 square root.
0.249.
0.249?
Yes, 2049.
2049.
My brain's still going on.
Rounding up.
Ounces.
205.
Okay. How do I interpret that?
On average, each mean of the sampling distribution varies by 0.2049 ounces.
Except,
Oh, wait, do you want it in like?
so what is that number? What is, this number represents the variability, right? Okay. Variability from what? What, and 10 represents?
The mean sample, the mean difference?
The difference, right? So you want to say this number right here will vary by this number of ounces, but you want to say that this is the difference, the mean difference. Okay? So you want to say,
Right.
on average, the difference, the mean difference, or the difference in ounces from the true mean of 10, because the true mean is 10. The true mean of one machine versus the one setting versus the other is 10. So you would say the average is 10, the average difference is 10. That number would vary by about 0.2049 ounces. So that means the difference here will vary by 0.2 of an ounce, or 1/5 of an ounce, I should say, not 0.2. That's the same thing. 0.2, 1/5 of an ounce. Okay.
Yeah. My phone died. I might have finished my run.
So interpret, calculate, and interpret. Okay. We'll finish the rest.